Take a look at these three materials. If we apply an electric current to each of them, we get three distinct reactions. We are often taught that materials exist in a strict binary, that they either carry electricity perfectly or they block it entirely. In reality, every material in the universe pushes back against the flow of an electric current to some degree, without exception. This inherent opposition is a measurable property called resistivity. Understanding a material's specific resistivity allows us to predict its physical behavior and integrate it into the tools we build. This is a logarithmic number line. Logarithmic scales allow us to compare values that are orders of magnitude apart on a single line, and we can use it to map the physical world based on resistivity. On the far left of the scale, we find the domain of pure conductors. Metals occupy this space. They have extremely low resistivities, measuring in the mathematically minute range of 10 to the -8th to 10 to the -6th ohm meters. An ohm meter is the standard physical unit used to quantify resistivity. Because that value is so low, electrons can slide through a metal's atomic structure with almost zero friction. By offering the path of least resistance, metals serve as our primary highways for electricity. Now look at the opposite end of the spectrum. This is where we find insulators, such as ceramic, rubber, and plastics. The mathematical scale here is staggering. These insulators have resistivities that are 10 to the 18th times greater than the metals we just mapped. Physically, this multiplier means the electrons inside an insulator are bound so tightly to their atomic nuclei that the electric flow is completely walled off. While metals act as frictionless highways, insulators act as impenetrable concrete walls. They create a physical universe defined by these two extremes. But look at the gap between those highways and walls. There is a vast, empty space in the center of our number line. This space is occupied by semiconductors. Semiconductors are materials with electrical properties falling between those of a conductor and an insulator. Under room temperature conditions, they are neither great highways nor perfect walls. However, they have a specific quirk. Unlike a typical metal, a semiconductor's resistivity decreases as its temperature rises. Sitting in the middle makes their properties highly adaptable, providing a foundation for engineering. Unlike most materials, a semiconductor's resistivity is adjustable rather than permanently fixed. We can modify this value through a process called doping. Doping refers to the controlled introduction of specific foreign atoms into the crystal lattice to change its electrical behavior. Adding these impurities drastically drops the material's resistivity, enabling the charges to move. This engineered drop allows us to control exactly when and where electricity moves, effectively turning the material into a microscopic switch. Stringing billions of these controllable switches together creates the circuitry for every modern electronic device, from computer processors to smartphones. Our modern world relies on our ability to mathematically engineer the resistivity of semiconductors.